And this is a roof design. In this case, it's for a blast freezer. And we want to calculate the bending, shear, and deflection for a roof panel when it's subject to gravity and wind loads. So we've chosen a panel, and it's called a Mathcad panel, and that's from Metalcraft. And here we've got a span of 8.85 meters. That's quite a big span. And our panel thickness here is 200 millimeters. We look at the tributary width, so we're looking at the unit width of the roof. And conveniently, that's how wide the panels normally come, as 1 meter wide. Sometimes they come a bit wider, but it's much easier to relate to a meter width. Skin thickness of these, in common with many of the panels, is 0.59 millimeters. The panel mass you can take from your lookup table from your brochure, or you can work it out. We then derive the second moment of area for the skin and the second moment of area for the panel using the parallel axis theorem as well. So from that, we can calculate the elastic modulus for the panel and the plastic modulus for the panel. And from that, we can later derive the elastic section capacity and the plastic section capacity. You will notice there's very little difference between the elastic and the plastic section capacity because it's all down to the steel plates in terms of bending capacity. The design shear capacity is down to the core. So again, we give the shear strength of the core and apply the strength reduction factor. Let's take our loading. In this case, we've got quite a number of services hanging off our panel. In this case, it includes sprinkler pipes. And so if you're ever designing these cool stores or warehouses, always ask whether they're sprinklered, because it makes a big difference to the load in there. So the loading of the services is bigger than the loading of the self-weight of the panel itself. We allow a nominal live load, but at a nominal, in this case, a nominal wind load. So look at the different load cases and load combinations we've got. We've got the typical ones, the combined dead and live, just dead on its own, and then dead plus positive wind, and then your dead plus the uplift, wind uplift. And from that, you will derive the design moment. Take the worst case and compare it to your capacity. In this case, it's very efficiently designed and that your utilization ratio is 100%. You'll see that the shear is similarly compared with the capacity, and it's only a utilization of 27%. Okay. A quick check at serviceability limit state. So we pull out our short-term and long-term load combination factors, and we derive the deflection, as you've seen from the equation before, under the combined dead and live loads, short-term and long-term. You can also check the deflection under the service load. I've set the wind load deflection and the dead and live load deflection to be span over 200. That's entirely up to you. It's a bit of engineering judgment as to what the live load deflection and the wind load deflection should be limited to. Most of the published tables will limit it to span over 150. And if you're looking at a freezer, then there's going to be a big difference between the temperature inside your room than outside your room. And that will cause thermal bowing. And here's a little calculation as to the deflection induced by your thermal bowing. Okay, this then goes on to connection design, but that's for another day. We'll move on to the wall design. So same sort of panel. In this case, it's a mere 125 mil thick. It's a Mathcad panel, and it's got a PIR core. So this is now a vertical panel, and it's subject to the roof loads, and it's subject to wind loads on its face. Same thickness of skin, and we've got the usual parameters of its capacity. We can derive the second moment of area for the panel and the radius of gyration needed. We can then derive the plastic section capacity and the elastic section capacity as before. We then calculate the buckling load and the elastic critical buckling load. I skipped over a nice little check on the panel slenderness. So we can do this panel slenderness check. Now our spreadsheet will tell you if it's more than 180, you've got an error. If it's more than 180, if your slenderness is more than 180, then you really need to think about the additional loads that are induced because of the slenderness. If it's below 180, they're probably not that significant. In this case, it's only a little bit above. So we have a little bit of an increase in the loading because of that. So once again, we take the loading. In this case, we've taken it from the roof and then we're applying it to the walls. We do our load combinations again, dead and alive, just dead on its own, positive wind downwards and wind uplift to get the worst case. We have an induced moment on all of these. Because you've got an axial load, you're saying that the load is applied at an eccentricity. This is a little bit conservative. We're saying it's applied at the face of the panel rather than directly in the middle of it. So from the geometric centroid of the panel, you then say it's a little bit off the distance from the next panel as well. So you're applying quite a big deviation, eccentricity, in this case 100 mil, which gives you an induced moment in each of these load cases. In many of the load cases, it's not that much, but it's not nothing. Then you want to check your wall panel for lateral loads. So the lateral loading or out of plane loading is usually the critical factor. And in this case, it's only taking wind, regardless of which direction it's in. And so you then take the worst case of the bending arising from the wind, and then you can compare that with your amplified moments from the axial load, and then compare the two. So compare your design moment with your plastic capacity. You'll see you've got a ratio of 60%. And you can look at the bearing, compare the applied axial load with the bearing area that you're assuming. So you're assuming the full width of the panel and the unit width length of the panel. And you'll see the capacity is fine. Again, shear is fine. We compare the applied shear, enhanced applied shear with this fiddle factor. Just pop back to see what the fiddle factor is. So this amplification factor is derived from the figures above based on your elastic critical load, and it only comes out as basically 1.038. So a small increase from your non-slender panel. And again, we apply the thermal bowing, and you'll see that's fine too. The next part of this sheet goes into connection design, which I'll reserve for next time. The final one is looking at using panels as beams. So here's the Mathcad for a panel beam design. So in some cases, you'll have openings and you won't really want to use a separate lintel. You can use the panel itself and turn it on its side and use it as a lintel. And the way you use it as a lintel is to employ the skins as your webs of your beam and apply a channel. So you rivet channel top and bottom. So we take our channel properties. In this case, it's a 150 by 45 by 1.55 steel channel. And we do the same for the bottom as well. We calculate the areas and the second moment of areas and the offset from the centroid. From that, we can derive, using the parallel axis theorem, the second moment of area about the neutral axis. If you don't like the units, you can always change them. That's the kind of joy of Mathcad. Have something slightly more sensible, it should change. If you don't like it in standard engineering form, you can change that into a decimal form. And if you don't like all the decimals, you can reduce the number of decimal places to make it more of a sensible number. So we work on the elastic section modulus of the compound section and derive the moment capacity based on that, including our wrinkle factor. So for our beam, we've said our beam is 600 deep, and it's the panel width. And that gives you a 15.6 kilonewton meter bending capacity. The shear capacity is based on the webs. And again, we use our wrinkle factor in there to give you a 23 kilonewton capacity. So you compare that with the applied bending and the applied shear, and you find out your utilization ratios are just about good enough. If you don't like it expressed like that, you can again change that to a percentage and reduce the number of decimal places. So you have a nice round. So keep a lookout on this channel. Please subscribe and share the show with your friends, and hit that like button on the bottom of each video.